Hello, this is Nick of Time. In our last session, we looked at the development of ether theories in the 1800s. Well, in the beginning of the 1900s, they developed a warped view of time and, of course, a warped view of the physics of space and time. The good news is that the inherent nature of time allows us to see that was a warped view and shows us how to correct that view and how to correct the associated physics. We'll first look at the relativity principle, which I often abbreviate as RP. There are two interpretations of the relativity principle. The currently accepted modern relativistic interpretation is that the relativity principle represents physical reality. And the consequence of that is that we have four-dimensional space-time where time morphs into space and space morphs into time. In addition, it gives the belief that all observer views are equally valid views of what's happening physically, even though those different observer views contradict one another. The alternate interpretation is that the true physics model is hidden, so that we're forced to use the relativity principle as a math tool to get answers for some physics effects. We can't get all of the physics effects because that requires knowing what the true physics model is. Okay, so what are the limitations of the relativity principle? Well, as we alluded to before, the relativity principle leads to the concept of the equality of all frames. And that leads to a frame-centric view of physics. But frames are just a math construct unless those frames represent unless a frame represents a physical entity where, for example, motion with respect to that physical entity causes physics effects. Well, frames and observers are not, in general, the causes of what's happening physically in space-time physics. So the paradigm that all frames are equal removes the preferred frame construct, which in turn removes the physical entity that's the key to physics and often associated with what is the true cause of that physics. So, why is the relativity principle liked by the physics academia? Well, I think the primary reason is that it's a general principle, and they like everything to be derived from general principles. Furthermore, they didn't like Lorentz ether theory, which was constructed on a coherent physical model, because as it happened, the preferred frame, the ether-rest frame, could not be identified. So, in fact, ad hoc modifications had to be made to the Lorentz ether theory. So why does the relativity principle seem to be confirmed by experiment? Well, there are a couple of reasons. The real physics is hidden. So the experimental results can't be compared versus what the real physics predicts and what the relativity principle predicts. Again, the real physics is hidden. So a model of the laws for a frame is developed from the empirical data. Then math transformations are derived to have all the frames use the same laws, i.e. to conform to the relativity principle. So what happens is all frames simulate being the single preferred frame. And that gives a result that is successful in some areas, but it's still limited in other areas. Okay, how do the limitations of the relativity principle manifest itself? Well, the relativity principle breaks down for proper time. Proper time is absolute, observer independent, operationally defined, and cumulative. So that the absolute physical model of proper time peeks through the facade of the relativity principle. Again, proper time is operationally defined. That means proper time is an excellent pure physics construct. It can't be subjected to mathematical modeling without any physical constraints. Secondly, it's cumulative, so that means that the physical characteristics of proper time accumulate and don't disappear, and that greatly facilitates the characteristics and properties of proper time peeking through and showing themselves, and the real physical model shows itself. Secondly, because in using the relativity principle, all frames simulate the single preferred frame, contradictions appear when comparing the views of multiple frames. We'll see that. We'll see some examples of that. Okay. Let's examine an example of how the relativity principle has been applied. Lorentz was correct about there being a preferred frame, namely the ether frame, for light and electromagnetic wave propagation. Then the Michelson-Morley experiment results that the ether frame could not be found led Lorentz to modify his preferred frame ether theory to have clock slowing and length contraction as a function of velocity with respect to the single ether frame. Then Einstein came and changed what was correct about the Lorentz ether theory by replacing absolute velocity with respect to the ether frame with relative velocity. Relative velocity with respect to each and every inertial frame. In doing that, he had every frame simulate being the single preferred frame in Lorentz ether theory. And he did that so as to conform to the relativity principle. But in doing so, he moved away from physical reality. So every inertial observer in Einstein's special relativity observes himself to be in the preferred frame of the Lorentz ether theory. Every inertial observer sees moving clocks slowing down and moving meter sticks contracting as a function of velocity with respect to their own rest frame. And obviously, when you compare different observers, you're going to find contradictions. Different physical results. So again, let's look at the key driving concepts that we talked about before. I changed it a little bit this time, and we're talking about observed constant speed of light. And that leads people to come up with the relativity principle namely that the physics laws are the same in all inertial frames, and that therefore all inertial frames are indistinguishable. Well, Einstein took it another step, and he said all inertial frames are equal. So, once again, thank you for stopping by. Hope to see you next time when we talk about the problems with the modern-day concept of simultaneity. And obviously, the concept of time and the concept of simultaneity are intimately bound together. So it should be interesting. Hope to see you.